Hello everyone, this is Kun Qian from Alibaba Cloud. I'm excited to present Alibaba HPN, a new network architecture specifically for LLM training. HPN has been largely deployed in Alibaba Cloud for around a year. It supports the interconnections of tens of thousands of GPUs and delivers excellent performance for thousands of model training jobs from many customers. Why we need a brand new network architecture? Let's start with the feature of traffic pattern. In our production, general cloud computing generates millions of flows, and traffic utilization generally stays below 20%. The overall traffic pattern is relatively continuous and steady. On the contrary, the LLM training generates very few but periodically burst flows, as shown in the figure. The bursts can reach the maximum unique capacity, which is 400 gigabytes per second. Therefore, maximizing bandwidth utilization in LLM training is crucial. A general cloud computing instance typically generates hundreds of thousands of connections. On the contrary, each node in the LLM training generates only a few dozens of connections. It makes load balance even harder. Second, LLM training is more sensitive to failures. Multiple GPUs cooperate for dozens of days to complete the entire training process. A failure on any GPU or host could crash the entire training process. In our production, each month 0.057% of links fail. In each month, 0.051% of switches encounter critical errors and crashes. Such a failure ratio brings non-negligible harm to LLM training reliability. In commodity data centers, the three-tier clause is the most widely used topology, which intrinsically introduces two limitations. First, it employs ECMP as the load balancing scheme. ECMP assumes that the number of flows is big enough so that the hash algorithm can effectively distribute the traffic evenly across all equivalent paths. This assumption is true under general cloud computing. However, it is no longer valid for LLM training. After multiple times of hashing, hash polarization would lead to severe load imbalance as shown in the figure. Furthermore, eliminating the root cause of failures is challenging. While the Tier 2 and Tier 3 layers have abundant redundant links, each NIC connects to a ToR via a single link, posing a single ToR single-point failure risk. A ToR failure can make dozens or even hundreds of hosts unavailable, leading to severe service quality degradation. Based on the unique characteristics of LLM training, we decide to build a new network architecture. It should meet the following goals. The first goal is scalability. To accommodate the requirement evolution in the coming future, we set the primary capacity goal of containing 15,000 GPUs. Considering the far future requirements, our additional capacity goal is to support 100,000 of GPUs. The second goal is performance. To enhance performance, our design should minimize network hops as much as possible. Reducing the number of hops lowers latency and decreases the time of ECMP hashing, making the path selection scheme more precise. The third goal is the reliability. Our solution should fundamentally avoid the failure of single ToR at the topology level. In traditional data center networks, two ports of each NIC are aggregated through one cable connecting to a ToR switch, called single ToR design. Single ToR is vulnerable to switch or link failures, significantly affecting the LLM training. To eliminate the root cause of failures, we decide to construct a non-stacked Dual-ToR design, as shown in the figure. Two independent ToRs work as a bond for each NIC. To synchronize these two ToRs, we make a series of modifications. First, we add an ARP broadcast module on each host to update ARP information concurrently to two different ToRs. Furthermore, we employ configurable LACP and converting ARP to host routes, which are inherently supported by vendors in the Ethernet community. Therefore, this design minimizes implementation complexity, significantly benefiting our production scale deployment. In addition, we leverage BGP for the inter-segment routing. When the NIC to ToR link fails, the corresponding ARP item will be withdrawn by the switch, as well as the corresponding host route, triggering the update of BGP. Therefore, the routing could convert to transmit traffic through ToR2. Next, let's consider how to build the Tier 1 network of HPN. The bandwidth capacity of the ToR directly determines the scale of Tier 1 network. We employ the latest 51.2 terabytes per second Ethernet single-chip switch in HPN. But why choose the single-chip switch, especially considering that multi-chip switches could support higher bandwidth capacity? Our long-term experience in operating data center networks reveals that multi-chip switches introduce more stability risks. The root cause is that multi-chip switches have more components and complex interactions among them. Specifically, our operational single-chip switch outnumber multi-chip switches by 32 times. On the contrary, the total number of critical hardware failures in multi-chip switches is 3.77 times higher than that in single-chip switches. Another design choice in the Tier 1 network is the real-optimized topology. The de facto configuration of a host is that 8 GPUs inside the same host are connected with a higher bandwidth intra-host network, like NVLink. Although the intra-host network bandwidth varies on the different types of GPUs, it is 4 to 9 times greater than the NIC bandwidth. To fully leverage different forwarding capacities, we deploy the real-optimized network. In a real-optimized network, NICs in the same rail are connected through the same set of Dual-ToR switches. NICs in different rails can communicate via a combination of intra-host and inter-host forwarding. Here, let's briefly review the topology in a segment. Two ports of each NIC are connected to different ToRs, and different NICs on the same host are connected to different rails. As a result, each segment covers the interconnection of 1,000 GPUs. With Dual-ToR in Tier 1 network, if we simply deploy a typical closed topology between ToR and aggregation, hash polarization would still exist. In the downstream direction, owing to Dual-ToR, there is a high convergence of traffic from 60 aggregation switches to 2 ToR switches, leading to significant performance degradation. Therefore, we propose the dual-plane design. ToR switches are categorized into 2 separate groups. With this design, once a flow enters the uplink of a ToR, its forwarding path inside a port is completely determined. Therefore, hash polarization is eliminated in the port. Thanks to the dual-plane design, when searching disjoint paths for optimal path allocation, we only need to search the links in each ToR switch, significantly decreasing the time consumption. This table illustrates the calculation cost under different network architectures. HPN can greatly decrease the computation complexity by 1 to 2 magnitudes. After deploying the dual-plane design, as shown in the figure, the ingress traffic of different ports becomes even. The queue length at the ToR downstream ports decreases by 91%. Through employing dual-plane in the Tier 2 network, the entire architecture of a port is shown in the figure. This table summarizes key mechanisms in HPN that contribute to expanding the network scale. With a Dual-ToR and real-optimized design, a single segment can cover 1,000 GPUs. With dual plan and the aggregation to core over subscriptions, HPN supports 15,000 GPUs in one pod. Considering the scale of tasks in production, a pod covers 100% of the training jobs we have served to date. Furthermore, to meet the long-term plan for supporting more GPUs, we have also designed the Tier 3 network, connecting multiple pods. In HPN, each host equips an additional NIC for front-end network access, and we designed an independent front-end network. We evaluate the training performance of 3 representative models under more than 400 GPUs. By employing HPN, the end-to-end training performance is improved by 6 to 14%. We further conduct experiments to show the reliability of HPN. As shown in the figure, a link failure occurs and the training halts immediately in single-ToR topology. On the contrary, with Dual-ToR, the failure of a single link only causes 6% performance degradation. This figure shows the impact of link flapping. In single-ToR, the temporary link flapping halts the training for more than 9 seconds. In Dual-ToR, the performance degradation is negligible. In conclusion, Alibaba HPN is a new network architecture specifically for LLM training. At the host side, we design non-stacked Dual-ToR access to avoid single-point failure. In Tier 1 network, we employ the latest 51.2 TB per second single-chip switch and a real-optimized network to containing 1,000 GPUs in a segment. In Tier 2 network, we employ dual plan to avoid load imbalance and support 15,000 GPUs in a pod. We believe HPN would be a good reference for constructing large-scale GPU clusters. And thank you for your listening.